Okay, here we are again. Since I'm not here, I'm going to go ahead and leave one of these videos for you so that you can kind of get an idea for what it is that's going on with what we're going to talk about today. Yesterday we talked about exponential growth and exponential decay functions. We looked at the example of the old man giving you the pennies every single day and how it actually ended up being quite a bit of money, because when things grow exponentially, they grow really, really fast. Or when they decay exponentially, they decay really, really fast. And we looked at the different shapes of the graph, and we looked at the different kinds of transformations. Hopefully you got your questions answered as we went over the homework assignment. Now, there is a way that we can come up with the equation for any exponential growth or decay function based on the situation. The exponential growth model looks like this. Let me get my pen ready here. The way that we figure out the model for exponential growth is it's going to be y is equal to a times 1 plus r to the t power. And now let's talk a little bit about what these things mean. Okay? A is always going to stand for your initial value. And make sure that you guys are getting all of this written down in your notes so you have it when you do your assignment today. A is always going to be your initial value. Okay? Now, R is going to be your rate of increase or decrease. It's going to be different whether we're talking about growth or decay. And then T is always going to be your time in years. And that's really important because the model doesn't work if it's not in years. If they give it to you in months, you have to convert that to figure out how many years that would be. Okay? Now, let's talk about exponential growth first. And that's actually exponential example B here. It says you bought a collector baseball card for $2 and its value increases by 5% each year. Now I want to kind of use this to help us make sense of this formula. Okay? I start with my initial value and I'm going to multiply that by the percentage of what I get to keep every single year that the value increases. Now, the mistake that a lot of people make is they just want to put 5% in there. We need this plus 1. And the reason for that is because if my value increases, if it's worth $2 right now, I get to keep 100% of that $2 plus the extra 5%. And then after the next year, I get to keep all of the value that I have, 100% of my value, plus that extra 5%. And so the reason that we have that 1 plus is this is the 100% that you're keeping no matter what. This is the rate of increase. So really each year, if it's increasing by 5%, I get to keep 105% of my value. So the way that we would set this equation up, we know that our initial amount is 2. That's going to be our A. And this percentage is going to be our R, but it has to be written as a decimal. Remember, 5% would be 0.05. Okay? Now notice we're not solving anything here, so they didn't give us time. We're just trying to write the model or the equation that's going to tell us about this. So to do that, I'm just going to plug in the parts that I know. I know that y is equal to initial value, which is 2, times 1 plus the percentage, which is 0.05, to the t for time. And if I go ahead and condense that down, I get a final equation of y equals 2 times 1.05 to the t power. And that would be the exponential growth equation that tells us that. Now, how could I use that equation to try and answer some questions? Let's say I wanted to know how much was it worth after 5 years. Well, you have to ask yourself, where does years go in this equation? It would go in for t. And then we would just use the order of operations. You would have to do exponents first, and then you would have to multiply by 2. And that's really important that you make sure you do that in the right order. We'll look at some examples of that in a minute. So let's go back up now to exponential decay, which is a little bit different, and we got to think about this the same way. The equation is always based on what we're keeping, okay? So if we look at example A here, which is decay, you bought a car for $5,000, a cheap car, and its value decreases by 20% each year. So if I'm losing 20% of the value, the question really is how much of the value do I get to keep? So if I lose 20, that means I'm keeping 80% of the value. And that is why the exponential decay model looks very similar, but it has one difference. You're going to do 1 minus the rate. Okay? Remember, if I were to write 100% as a decimal, it would be 1.00. So what we're saying is take 100%, subtract the rate that you're losing, and that's going to leave you with the rate that you're actually keeping. So in this case here, I would have y equals, what's the initial value? It's 5,000, so that's what we're going to plug in for A, times 1 minus, remember we need to write this rate as a decimal, so minus 0.2 or 0.20 to the t power. So if I am to rewrite this in its simplest form, that would be y equals equals 5,000 times 0.8 to the t. And if you look at these two equations and look at the rate of change there, you can see that it follows our rules that we know. If it's between 0 and 1, it's going to be exponential decay, and this is talking about a decrease in value. If it's greater than 1, it's going to be exponential growth, and here we're talking about an increase in value. So that's how you would set these up. Now, an extension on this exponential growth model, and this is what I started alluding to yesterday a little bit, is compound interest. But you know what? Before we go on and talk about compound interest, I want you to go ahead and finish up your assignment from yesterday. You did 1 through 6 for homework last night, and what I would like you to do is finish it up and do 7 through 11. Those are going to be models of exponential growth and exponential decay. Now, go ahead and get that paper in front of you really fast because I just want to tell you one thing here. If you look at, for example, number 9. Now, we've done problems like this before when we looked at the scatter plots. If you look at number 9, it says from 1997 to 2002, the number n in millions of DVD players sold in the United States can be modeled by, and then it gives you the equation, where t is the number of years since 1997, okay? So we're going to be counting t starting at 0. T equals 0 means that I'm in the year 1997. So if I wanted to show that it's 1998, how many years have passed? 1. So that's what I would use for t. It's a question of how many years have passed. So when it wants to know in part B how many were sold in 2001, well, how many years are there between 97 and 01? 98, 99, 2000, 2001. So you're going to plug in 4 for t in that case. Hopefully that clarifies that a little bit. So do the best you can on those, and then we'll come back and talk about compound interest in just a few minutes.